So my talk is on Nilpotent. Okay, so right. So first of all, nice to be here in France virtually, and thanks to the organizers for inviting me. My talk is about, or my title is Nilpotent Endomorphisms of Expansive Group Actions, and this is some joint work with Ilkka Törmä. And so I will explain all the words in the title in due time, but basically all the difficulties we have here already arise in cellular automata on groups in the sense of Ceccherini, Silberstein, and these guys. So that you have a full shift on some group, and then you have an endomorphism of that. But we generalize a bit because we can do that more or less for free. But the direction of, so the word group here is the most important. So the generalization to groups is where we have the most trouble. Okay, and so the theme here is more or less that cellular automata, we see them as dynamical systems, and they are pretty complicated to study. So one thing you can do with them is that you study cellular automata which are somehow very, very simple. And when I say very, very simple, I mean like ridiculously simple. So imagine the dynamics like this. You have your phase space, and in your phase space you have a black hole, and all the dynamics does is it sucks everything into the black hole. So there are various precise definitions for that, which I will give in a moment. The strongest one is that everything is literally mapped into the black hole in finitely many steps, and then you can have slower convergence and so on. Okay, so is it possible to change slides? Oh, here, maybe. All right. Do you see slide number 2? Am I a robot?
Yes, we
You're
see
still hearing me.
2.
All right. Okay, and you still hear me all right. Okay, so let's start with some definitions. So I will deal with dynamical systems, topological dynamical systems, and one thing is that my dynamical systems are always pointed, which just means that we pick a point in there. So every system I have has some kind of 0 point, and it's somehow part of the structure, so everything preserves that and so on. So here's some detailed definitions. So I always have a group acting, or I have the natural numbers acting. A pointed topological dynamical system is that you have the group or n, and then you have your topological space, and then you have a 0. The space is compact metrizable, or even compact metric later, and there is a 0 point, and then your m acts continuously on x. My convention is from the left, and the 0 point is fixed. 0 is called the 0. Sometimes it's omitted in the notation. When M is a group, we think of M as acting by spatial translations. This has no mathematical meaning, but usually we think about subshifts, and then the subshift is kind of you have a group which acts by subshift translations, and then when M is the natural numbers, it is a cellular automaton which gives you like a temporal dynamics on the space. And usually we have a commuting action of these two, and we write the group on the left and F on the right. F acts from the left, but it doesn't matter because N is abelian. Okay, so that's some basic definitions. Here's some more specific definitions. So just for convenience, write 0 also for the constant 0 function, mapping everything to 0. And now we can very quickly state the various definitions of nilpotent. So nilpotency always refers in this talk to n actions. So a pointed dynamical system is nilpotent if there exists an n such that f to the n is 0. So this is what nilpotent means in a monoid or in a ring usually. Or I mean, okay, it can mean various things even in that context, but still. And then you have asymptotically nilpotent, which is what it sounds like. So every point converges to 0 or the black hole. And then you have uniform asymptotic nilpotency. Every point tends to 0 in a uniform way. So after some n steps, every point is at distance epsilon from 0. So nilpotent and uniform asymptotically nilpotents, or UAN, these of course imply that the action is not invertible. Asymptotic nilpotency is possible even if the action is invertible. Okay, and here's a important definition. A family of NPDS is nilrigid if every system in the family is either not asymptotically nilpotent or it's even uniformly so. So for all of the systems, AN implies UAN. So that may seem strange, but it is useful because we talk about these families a lot. And also, we say that a single system is nilrigid if the singleton family is. So we say a system is nilrigid if it's not asymptotically nilpotent at all, or it is uniformly so. Okay, so those are kind of funny definitions, but that's what nilrigid means for us. Okay, so one-dimensional cellular automata, the most basic setting. So a pointed one-dimensional full shift is a to the z, and you have a 0 point, which is just the all 0 configuration, and 0 is some element of the alphabet. The action is by translation, so you have here you have the group Z acting, and the generator 1 acts by the left shift, which we also write as sigma, and A is the alphabet. I should maybe be skipping some of these, but cellular automata were not discussed so much, so I will not. A pointed cellular automaton is a sigma commuting continuous map, which satisfies the 0 maps to 0. So I mean that the all 0 configuration is mapped to the all 0 configuration, but individual symbols could turn into non-zero symbols in the action of the CA. And maybe some of you know that cellular automata have local rules. Those will not play much of a role here because I will not go that deep into the proofs. But cellular automata have local rules, so the new value at a group element will be specified by looking at some neighborhood of it. Okay. So it is equivalent to this definition. So here's an example of a cellular automaton. You take as the alphabet the 2-element group, and then you define by this rule a shift commuting continuous map. So the value at I is obtained by summing the value at I with the value immediately to the right, and this gives you a new configuration, and we call this the XOR CA. It's one of the most studied cellular automata probably. So here is a so-called space-time diagram. So black squares are 1s, gray squares are 0s, and the ith row from the top denotes fi of x. So you have a configuration. I only write the finite portion because the slides don't allow infinite ones. So here I have a single 1 surrounded with 0s, and then here you see what happens when you apply the CA repeatedly. So this one gives you very simple diagrams in the sense that they can be understood quite well with the tools of algebra, but typically you will see more complicated things. In this talk, you will see much more simple things. So XOR is not asymptotically nilpotent, so it doesn't really fit our setting. So here's some cellular automata which are much simpler and much closer to nilpotency. Again, I managed not to. Okay. So the 0 map is an example of a nilpotent CA. So everything literally maps to 0 in one step. Okay, not a very exciting cellular automaton. Here's a slightly more exciting cellular automaton. You take 0, 1 as the alphabet, and then you define by this local rule a mapping on A to the Z. So the new value at I is obtained by looking to the left, looking to the current cell, and looking to the right, and then you take the minimum of these. So if there is a 0, it is going to be copied to its neighbors, but if you see 3 1s in a row, then the central one stays a 1. So this is almost asymptotically nilpotent in the sense that if you take any configuration except the all 1 configuration, then it's going to tend to 0, because if you have a single 0 somewhere, it's going to start spreading and it's going to fill the whole configuration. So this is almost asymptotically nilpotent, but it is not asymptotically nilpotent because there is a single counterexample. Okay, so here's a nilpotent example due to Guillaume Tessier. So here you see a space-time diagram. It's very small because we don't really have to know its details. Here the alphabet is of size 3, and this color is 0, and the rule is something unspecified. We know here that f to the 18 is not equal to 0 because of the space-time diagram where we see a non-zero symbol on the step 18, but we know that f to the 26 is the all 0 map if we trust Guillaume's program, which I do. There are some other examples like this, but the rule is always pretty complicated. Okay. So, and then another thing, which is another near miss for nilpotency or asymptotic nilpotency, is that Ilkka Törmä has these examples where the spatial density of ones always goes to 0, or the spatial density of non-zero symbols always goes to 0 uniformly in the. So you tend to the zero map in the Besicovitch topology, but these are not asymptotically nilpotent. So the point is, there exist nilpotent cellular automata which are not completely trivial, and you can have some near misses to asymptotic nilpotency. Sorry. You can have some near misses to asymptotic nilpotency which are not nilpotent. Okay.
Sorry,
so
can you quickly say what is the Besicovitch topology?
The Besicovitch topology is that it's a pseudo metric on the configurations where you count the number of differences in a window from -n to n, and then you let n go to infinity, and you take the lim sup. But it doesn't really matter. The point is that the density of zeros tends to 1 in a natural sense.
Thanks.
So in Ilkka's example, you start with any configuration and you start iterating the cellular automaton. Then in a very uniform sense, you will see almost only zeros. There are a couple of individual ones which sort of look for each other, and somehow globally they manage to make this work. That sort of thing. Okay, so a quick history lesson. Nilpotency of cellular automata is undecidable. If I give you a local rule of a cellular automaton, you will not be able to tell whether it's nilpotent or not. This was proved in 1974 by Under and Lewis. It was asked in 1988 by Chulik, Paul, and Yu, and then it was proved in 1998 by Jarkko Kari. And this is a basis of many undecidability results. So many things which are known to be undecidable for cellular automata are proved by reducing nilpotency to them. So you prove they cannot be solved because nilpotency cannot be solved. For example, last year, Jalonen and Kari proved that conjugacy of cellular automata as dynamical systems is undecidable using this. Okay, so here's the first nilrigidity results, which are the present topic. So first of all, here's a trivial fact. A cellular automaton, not a trivial but easy fact, or I mean a simple lemma. A cellular automaton is nilpotent if and only if it is uniformly asymptotically nilpotent. So I gave two different definitions, or I gave three definitions. Two of them are equivalent, and this is very general in the sense that it almost always happens in a cellular automaton context. So here's the proof. After n steps, every point is close to 0, so therefore the entire spatial orbit is close to 0, and then these systems have a dynamical, the spatial action has a property called expansivity, which literally says that then the point is 0. If the whole spatial orbit is close to 0, then the point is 0. So in a very general setting, just using the word expansive from the title, we have that nilpotency is the same as uniform asymptotic nilpotency. So now we're left with two definitions. We have nilpotency, which is the same as UAN, and then we have asymptotic nilpotency, which is convergence to 0, but not necessarily uniformly. And we want to understand the connections between these two definitions, basically. So Guion and Richard proved in 2008 that cellular automaton one-dimensional full shifts are nilrigid. So every cellular automaton which is asymptotically nilpotent is nilpotent. So the near misses I reported, which were not asymptotically nilpotent, they could not be made asymptotically nilpotent without actually having them be roots of the zero map. And this proof is what we are trying to generalize here, basically. So their proof is very specific to full shifts, or slightly more generally transitive SFTs on Z. And I've spent quite a lot of time trying to generalize that to, for example, all groups and so on. They asked about the two-dimensional or the D-dimensional thing, but not other groups. Okay. So I will need some more definitions. So the full shift is A to the G. So you take colorings of the group by the alphabet. So again, the finite alphabet, and there's always a 0. And the action is like this. I think we use another convention in the paper. There are 8 different conventions, I think, which you can use. Some are better than others. So in this convention, you should think of the left calligraph, and the translation by G moves the origin to G. So the new origin is G, and now you are kind of there locally. A subshift is a closed G-invariant subset of a full shift, so it means that it also has a combinatorial characterization where you forbid some local patterns from appearing in the left calligraph point of view. A subshift of finite type is a subshift of this form. So you take a Klopen set, so some set which only talks about finitely many coordinates, and then you require that everything is in the orbit of that. So you take those points of A to the G whose whole orbit stays in C. Okay, so that basically means it's the same as a tiling system up to isomorphism, dynamical isomorphism conjugacy. A subshift is suffix if it's the image of an SFT under a shift commuting continuous function among subshifts. A point here, so here's something less standard. A point is homoclinic if its spatial orbit tends to 0 as G tends to infinity in the sense of the 1-point compactification. So as G escapes finite sets, you get closer and closer to 0. In the subshift setting, you can state this in another way. So the support of a configuration is those G where xg is not equal to 0, and homoclinic points are just the ones where the support is a finite set. So you have 0 except for a small area in the left calligraph. A cellular automaton, so again, 0 is part of the structure, so this makes sense. So a cellular automaton in general is again a shift commuting continuous map, so it is continuous and it commutes with the action of G. And by default, when I say cellular automaton, I mean it's a cellular automaton on a full shift, but we also study them on other subshifts, which just means it has the same combinatorial definition and the same general definition. It's just that you have to preserve the full shift. And when there's a 0, it is again preserved. The all 0 configuration is preserved. Okay, so one example of an SFT is the full shift itself, and here the cellular automata are very easy to enumerate. You take a finite subset of the group, you take any function from A to the B to A, and then you define using this formula a cellular automaton. So the new value at G, by looking at the neighborhood of, if you open up this formula, it looks at BG, where B runs over uppercase B. So you look in the left calligraph, you look at the neighborhood, and that you have some rule for determining the new value. Any rule gives you a cellular automaton, and this gives you exactly all the cellular automata as B runs over the finite sets and F runs over the functions. Nil rigidity for cellular automata on abelian group. So this answered, this was one of my first non-trivial results. So in math, this answered a question of Guillaume and Richard. So the first one is trivial. So in a one-dimensional SFT, cellular automata are nil rigid. This is almost the result of Guillaume and Richard, except that you apply it in the transitive components of the SFT. Okay, so nil rigidity for cellular automata on one-dimensional SFTs. Okay, so if G is Z to the D, and you have an SFT with dense homoclinic points, so any finite pattern can be extended somehow and then with zeros, basically, then cellular automata are nil rigid. So this was from 2012. So here there was kind of a new cool idea, sort of. So the idea is to take Z to the D, and you see this as a direct product of Z to the D minus 1 times Z, very fancy. And then there's something called periodization, which means that you take a configuration which is homoclinic, and then you take a lattice in Z to the D minus 1, and then you just copy paste this pattern in the Z to the D minus 1 direction. So this kind of drops the dimension to 1 in the sense that you have a now the cellular automaton will preserve this periodicity. So effectively, all the non-trivial things will happen in the Z direction because the Z to the D minus 1 direction will stay periodic. So this allows you to go from D dimensions to 1 dimension, and this sort of reduces nil rigidity. It reduces to nil rigidity in D dimensions to cellular automaton 1-dimensional SFTs where we have the result. And then there's a lot more tricks, which I will have to talk a little if I have time. I will have to discuss them a little if I have time to do that, but I probably don't. So here I will just say that the periodization is the main idea. So from this, it's easy to conclude the result for all abelian groups. So cellular automata on all abelian groups on full shifts are nil rigid. So and one mention is that strong irreducibility implies dense periodic points in the pointed setting, and as I said earlier, strong irreducibility is very close to the kind of thing which Nishant was talking about. So you can take patterns, and as long as they are separated from each other, you can glue them together. So very weak versions of that imply dense homoclinic points in the pointed setting. Okay, so then the main question is, for which finitely generated groups are cellular automata on all G full shifts nil rigid? Is this maybe true for all groups? I don't know. So here's a partial picture of families of groups. So finitely generated groups are a rather complicated zoo, so we like to give names to different species of them. And so here on top I put all of them, Sophic and Amenable and Aleph, but those are just here because I know that there are dynamicists in the audience, and you only know this. You may only know. I mean, of course, everybody knows everything, but maybe you like these guys on the top more than the ones on the bottom because these are too easy or too small. But we are really dealing with these ones on the bottom. So here the easiest groups are the abelian ones. So finite ones are too easy to discuss at all, but abelian ones are just right. So you have Z and Z squared and so on. And then just on top you have the nilpotent groups, which are the groups where the lower central series is a central series, but I will not give the definition other than that. So the Heisenberg group, which is the upper triangular matrices with ones on the diagonal, which are 3 by 3 and which are over integers. Okay, that's the Heisenberg group. It's a central extension of Z squared by Z, and so it's kind of a three-dimensional grid, and the top direction goes very as you'd expect, but then the Z squared arrows are sort of wonky, so it's kind of a weird grid between 3 and 4 dimensions or whatever. And anyway, then there's the polycyclic groups, and these are sort of what you get by extending Z by copy. So you start with Z and then you start extending by adding Z many layers on top and so on. So this is kind of what you get from Z by group extensions with other copies of Z. And then these are residually finite. I will define that soon, and they are also solvable. And then on top there's the elementary amenable. I will give the definitions in a moment, but just some groups. I mentioned the Heisenberg group is here, and then here just above polycyclics there is the Lamplighter group Z, which is Z acting on the infinite direct product of Z square Z2s, and that's both solvable and residually finite. Here in residually finite you also have the free group, which is one of the open cases left, and then just above you have S infinity R times Z, and this is not residually finite, so this is also beyond our capabilities. Okay, but okay, so let me now tell you the result. It's just at the 20-minute mark, so I hope nobody left yet. So here's our theorem published or accepted last year. So let G be a locally residually finite and poly locally virtually abelian group. Okay, so G belongs to some crazy family of groups, which I will tell you more about in a minute. And then there's a couple of dynamical assumptions. So you assume that Gx0 is an expansive zero gluing pointed dynamical system with dense homoclinic points. Expansive I sort of almost defined already. Zero gluing is a kind of new notion. It only appears in this paper and in some other papers of mine. And then you need this dense homoclinic points assumption. And in this case, all endomorphisms of this system, so all self-maps which are continuous and commute with the G action, are nilrigid. Here's a slightly more palatable corollary. So if you have a residually finite solvable groups, for example, the Lamplighter group or the Heisenberg group, you have any expansive pointed dynamical system which has the shadowing property or the POTB property and dense homoclinic points, then endomorphisms are nilrigid. In the zero-dimensional case, which is closer to this conference, I guess, in here expansive and shadowing is the same as SFT. So we are just saying that if you have a pointed SFT with dense homoclinic points, then endomorphisms are nilrigid. So in particular, if you have a residually finite solvable groups, then endomorphisms of the full shift, the pointed full shifts, are nilrigid. Okay. Here's some definitions. So expansive, again, it means if you have 2 points, which so if there exists an epsilon such that whenever 2 points throughout their whole joint orbit stay epsilon close, then they're actually the same point. And an endomorphism I defined many times already. So it's a continuous map which commutes with the G action. And endomorphisms of subshifts are by definition the cellular automata. Okay, and zero gluing. So this is a slightly more complicated notion. I don't know if you can really understand this if you don't know what shadowing is, or I mean, if you, maybe you can understand it. I wouldn't be able to understand it if I didn't know what shadowing is. So this is close to the definition of shadowing on a group action. It's kind of shadowing when close to zero. So it's a slight. So in the subshift case, it's a slight generalization of an SFT, where you can have very complicated forbidden patterns, but they cannot see over a sea of zeros. So you can check a very complicated condition, but if you kind of separate your configuration from another by zeros, then your forbidden patterns cannot see over the sea. So here's the general definition. You have a dynamical system, and you have a group acting from the left. If you have a finite, an E denotes a finite subset, A denotes some subset, and delta is a constant. You write partial E of A for the inner boundary of A, so those G which get out of A by a left translation by E, and a delta E designation is a set of pairs AI xi, such that G is partitioned by these AIs, and whenever G is in the boundary of AI, then you have to be delta close to 0. And then you have an epsilon realization of a designation is just a point which inside AI copies its behavior from xi. Okay, so basically you split your group, or the left Cayley graph maybe, into pieces, and in these pieces you can pick anything that you can see in a configuration, except that near the boundary you should see zeros, and then a realization is a configuration which is literally just obtained by gluing all of those things together up to some the epsilons and deltas. And zero gluing, so in the subshift case, it literally means that you can glue pattern. If your patterns have zeros around them, you can glue them together freely. And zero gluing means that for all epsilon there exists a delta and E such that every delta E designation has an epsilon realization. That's the usual order for you would see in this context. So when shadowing and POTP implies zero gluing, but not vice versa. So in the subshift case, SFT implies zero gluing. So that's a weaker assumption than SFT. Okay, so now onto the group definition. So a group is residually finite if one of the following equivalent conditions holds. So first of all, the right definition, sort of what we use in other algebras, is that at least in some context. For every finite subset of the group, there exists a finite quotient, so a finite group H, and a homomorphism, which is injective when you restrict to F. Okay, so you have your infinite finitely generated group in my context typically, and then you want to find a quotient, so you want to kind of turn it into a finite group in a nice homomorphism way, and you want that some finite ball is actually embedded in this homomorphism. So that's residually finite. And then another equivalent one is that for every non-identity element, there is a finite index subgroup which misses that. This works in the finitely generated context. It happens to be equivalent to full shifts having dense periodic points. So points with finite index stabilizer being dense. And it's actually the same as saying that expansive zero gluing PDS with dense homoclinic points have dense periodic points. So exactly with my assumption, you will get dense periodic points, and dense periodic points are what's going to be important. And there was also some other stuff. So if you have a class of groups, we say G is locally C if every finitely generated subgroup is in C. Actually, sometimes people use this for a slightly different thing, but here it's equivalent. So for example, with my definition, Q plus would be locally free, because if you take any finitely generated subgroup of Q plus, well, it's going to be Z, right, up to scaling. So that's locally free because Z is a free group. And then a group is K by H if there is a surjective homomorphism from G to H with kernel isomorphic to K. And in this case, we say G is a group extension by one of the groups by the other group. And if C is a class of groups, poly C would be the class of groups which admit a subnormal series. So just a list of groups where each one is normal in the next one, such that each quotient of successive terms is in C. And this happens to be equivalent to saying that it is the smallest class of groups which contain C and which is closed under group extensions by a little undergraduate lemma. So a group is polycyclic if it is polycyclic. Okay, so if it can be built from cyclic groups by group extensions, more or less Z's, because everything is up to commensurability here. So it's more or less what I said previously, but you would allow finite cyclic groups in here as well, in general. So unsolvable just means polyabelian by definition. And a group is virtually C if it has a finite index subgroup in C, and so usually in this context, virtually has virtually no effect. So if you're virtually C, you can just think that you are C. So again, here's the group picture. So now we can say where our groups lie. So they will be somewhere in here. More specifically, you have the elementary amenables and the solvables, and between you have the locally virtually abelian groups. So those groups you can build by group extensions from groups which have all finite degenerated subgroups virtually abelian. And plus here you have the residually finite groups, and then our groups are the intersection of these two classes. There are some groups here which are not solvable, and there are of course solvable and residually finite groups which are not here. So this is more or less a good representation of where our groups lie. There are certainly also non-polycyclic groups there. So here are some examples. Our class of groups includes every linear group which does not contain a free group by its alternative, every virtually nilpotent group, so the same as polynomial growth. It also contains all abelian by polycyclic by finite groups. This is by this guy and this guy. It also contains every wreath product where you have an abelian group and a polycyclic group acting on it. So for example, it contains the lamplighter group. So this was one of the examples we wanted to cover because everybody loves the lamplighter. There are also several classes of groups which are not virtually solvable. You will find some of them in our paper, and then there's a Math Overflow post where Yves de Cornelier gives a couple more. But there are many, I think. And also the dynamical, there were also some dynamical properties, so we can also come up with some non-full shifts where these things apply. So yeah, so there was the full shifts. So on full shifts on groups, all endomorphisms are nilrigid. If you have a finite degenerated group generated by S, then the golden mean shift defined like this. So if you have a 1, then you shouldn't see another 1 in the S neighborhood. So this would be also a subshift of finite type. And this is easily seen to have dense homoclinic points. For example, it's strongly irreducible and it's a down subshift. So many ways to show that. And then here's an example, which is an SFT with dense homoclinics. To recall that SFT plus dense homoclinics, then our theorem applies. So these are not strongly reducible. So you require that if you see 3 ones like this in a non-completed square, then the completion to a square should also have a 1. So this is one of those many SFTs where everything consists of some kind of rectangles. So here also all cellular automata would be nilrigid. And then another example is so if you have any group and you have a proper suffix shift, so a suffix shift which is not itself an SFT, and if the SFT cover satisfies that the 0 point has only one pre-image, so we call these 0 to 0 suffix, then these kinds of things are zero gluing, they're not shadowing. So if in a 0 to 0 suffix homoclinics are dense, then our result applies. So this is an example where it applies beyond SFTs. And also the Z action. So here are some positive dimensional examples, not so relevant for this conference maybe, or I mean I guess there are people who here also who care about these things. So if you, for example, the hyperbolic toral automorphism is expansive, maybe it's shadowing by a result of Bowen. It's expansive almost trivially, and it's easy to see it has dense homoclinic points, and the same is true for the ×2 map on the solenoid. So for these guys, all endomorphisms which are asymptotically nilpotent would be nilpotent. It turns out that that's a trivial fact, but anyway, our general theorem does cover both of these classical examples. Okay, so the rough idea is this. We use the periodization idea from my paper, but after that, it's quite a bit of a tour de force. Basically, I went to Ilkka one time when we were having lunch, and I told him, let's just take my idea and let's do all group extensions with that, so we get a large class of groups. And then Ilkka immediately tells me that this will not work because of blah blah blah, and then I was like, no, we have to do it. And then we started digging, and eventually we did it, but there are a lot of things we needed to do, a lot of new things, some of which are technical and some are really new ideas. So basically here the idea was to take Z to the D to be this direct product, and we replaced that by a group extension like K by H. And now it turns out that when you do the induction step, you just say, I will do the same inductions. I will do the induction step. It turns out that you have to do you have to prove a rather general thing to be able to make the induction works. And for this, we define the so-called tiered dynamical system. So we start with endomorphisms of dynamical systems, but we actually have to consider endomorphisms of a stack of dynamical systems somehow, because expansivity is very important. So a tiered dynamical system will be a dynamical system in itself, sort of, but because we need expansivity, we need to have somehow layers where we have expansivity, and that leads to really needing a notion of tiered dynamical systems, which I will define in the next slide, and their evolutions. And the idea is that we define these things and we define all the notions for tiered dynamical systems, and then we prove some closure properties. So we prove closure under extracting the periodic points along a subgroup. So this is kind of a generalization of the idea that you take d to the -1, and then you take a finite pattern and you glue it along a lattice. So the same works here. K is actually a subgroup of the group extension. So you can take, and because everything is residually finite by our assumption, more or less, let's stick to finite degenerated groups, then it was an assumption that this is residually finite. So then K would also be residually finite because it is a subgroup of the group extension. So therefore in K you can find finite index subgroups which are more or less the right lattice. And now if you have a finite pattern, then you can copy paste it into a finite index subgroup of K. So that gives you the periodization idea. And then we prove that our family of systems is somehow closed under this operation. And then we have to extract the points where information does not spread away from a subgroup with something called the fin construction. And this is something where we really need to have a stack of dynamical systems. I will not really have time to explain this stuff, but okay, anyway, the idea is that we prove that for a large class of groups, evolutions, which are more or less endomorphisms, evolutions for all systems are nilrigid. And we prove this by induction. If G is K by H, then we apply the fin construction to get a K subshift, and we apply it there. And then we apply the fixed construction to get an H subshift, and then we apply induction there. And then somehow we get the result for G from that. And it specializes to the main theorem for single tier systems. So here's the definition of a tiered dynamical system. So you have a triple, you have an X, and then a bunch of dynamical systems, and then you have a bunch of group homomorphisms. So here X is a compact metric space. Here it's really a metric space. So we fix a metric. So it's called the ambient space, and it contains again the 0 point. D is a directed set. You can think, for example, that it's N. And for each tier in D, you have an expansive pointed dynamical system, and all of them must contain the 0 point. We want that for every pair, whenever you go from layer T to a higher level T prime, you get more points. So these things are bigger and bigger. And when you go up a tier, you may have different groups on different levels, but the T prime group homomorphs, or it epimorphs onto the GT group, and this group homomorphism is finite to 1. And then you want that the natural diagrams commute, so these restrictions make sense. Okay. Oh, by the way, I have a little clock malfunction because I didn't remember when should I stop.
Good question.
Sorry? Never. Okay, maybe write it in the chat if you have an answer. Anyway, so, and then we also want that you have this natural property that the action of the group G prime is the same as the action of GT when you can apply both. So basically, if you have a point in the T tier, XT, then you can apply the group GT to get somewhere, and then you can also apply an element of GT prime by taking the homomorphic image and then applying that, and you just want that the result is the same. So these are just kind of natural things we assume from the stack of dynamical systems. And an evolution map is just a continuous map which commutes with the action when this makes sense. So if you start from tier T and it maps it to tier T prime, which is higher, then you want that this formula holds for G in GT prime, which is the set of elements where you can apply it to Fx. And we say that a tier is f stabilizing if when you start iterating f, you don't get higher than that tier. So you have a tier t, and this is f stabilizing if there exists a higher tier, so that when you take any point in xt, you start iterating the f, you don't get further than xst. Okay, and we say that an evolution is f stable. Sorry, yeah, we say that the system is f stabilizing if every tier is stabilizing, and we say that the when we write f here, it's called an evolution of a tiered topological dynamical system, or an ETTDS. Okay. And okay, so then I have some technical notes, and now again, I would like to know how much time I have to know.
So if
to what extent I'm going to cover.
At 40, at the most, that would be great.
Stop at 40. Okay, yeah. So I will try to spend some. Okay, I will just do what I do. Okay, so again, so let me try to explain a little more about the proof in the abelian case. So give you some of the technical ideas, because understanding why we need to generalize to tiered dynamical systems kind of requires you to know the proof. Of course, I will not be able to give you the whole proof because you would fall asleep, because it's too easy. But I can give you some of the ideas. And so one of the main ideas is this periodization. So let's go through that in detail. So let G be the group Z squared. So here it's so you have a vertical Z direction, and then you have a horizontal Z direction. So it's Z by Z. And then you have a Z squared SFT. So just a normal subshift of finite type in 2 dimensions. So some forbidden patterns. And then you have an asymptotically nilpotent cellular automaton. And recall that what we want to show is that f actually has to be uniformly asymptotically nilpotent, equivalently nilpotent. So we assume that every point tends to 0, meaning no matter what you start with, in the origin you will start seeing eventually bigger and bigger balls of 0, which never turn back to non-zero symbols. So that's what we assume. That's asymptotic nilpotency, and we want to show that this implies that everything actually maps to 0 after finitely many steps. Okay. So here's what we do. We take Kp, which is this subgroup of G. So you take just an arithmetic progression in the vertical direction, 0Pn, where n runs over the integers. Now, if you have a cellular automaton on the subshift, on the SFT X, this actually gives you a cellular automaton on Yp. So what do I mean by that? Well, so Yp is the points in X which are Kp periodic, and you can think of Yp as being a one-dimensional SFT. Why is that? Well, you periodized in the vertical direction. You only look at those configurations which have this vertical period, but now you have the horizontal period. You have the horizontal direction, and the action of that also it acts on the vertically periodic configurations, and actually. Up to isomorphism, that is a one-dimensional subshift of finite type, more or less by definition. So adding the period actually adds you a 2-dimensional forbidden pattern, and then all you have to check is more or less expansivity, and the horizontal action is expansive on Yp because you only have to look far enough to see the repeating pattern in the vertical direction. Okay, so this guy here is really a one-dimensional SFT under the horizontal action, and because a cellular automaton commutes with the shifts, it preserves Yp, so it actually gives you a cellular automaton on this one-dimensional SFT. And now, because the original cellular automaton is an, meaning in every configuration of the 2-dimensional SFT, it tends to 0, it means that actually it has to be a asymptotically nilpotent cellular automaton also in here, just because this is literally a restriction of the original. But now it follows from nil rigidity that this whole space of Kp periodic configurations is literally mapped to 0 after some finitely many steps n, by my slight generalization of the Guion-Richard result. Okay, so that's non-trivial, but it's true. Okay, and that's our main tool. And unfortunately, to explain where we use the tool, there's a little more. So once you have the previous observation, now you have 2 cases. So I will give you a general definition first. So if you have a normal subgroup of G, so that would be the Kp group, or generalization of that. And now if you have a cellular automaton on A to the G, we say information cannot spread arbitrarily far from the normal subgroup K if this thing here happens. So you have a finite subset of G such that for any configuration and for any n, the support of f to the n of x is contained in here. So what does that mean? It means that the set of cosets of K which touch the support of x only blows up by a little bit. So because K is normal, it is very easy to understand what this means. So you have kind of a shadow when you forget this kernel. You have a homomorphism, and then you can see which positions in the quotient have something in their fiber. Okay, and then you say that in this that the shadow will not be expanded by much when you apply. That's what it means to the information cannot spread arbitrarily far from K. And now we have two cases. In the case of z squared, if information cannot spread arbitrarily far from the vertical subgroup or the horizontal subgroup, so you apply the argument because z can be split into a direct product, of course, in two different ways. So it happens that if information cannot spread arbitrarily far, then actually 0 is a Lyapunov stable point because information cannot spread arbitrarily far in the horizontal direction or the vertical direction. That just means it cannot spread at all. And if information cannot spread, that more or less means that 0 is stable. So if you see a big bunch of zeros, then you will never be able to send something non-zero in the center of it, and then it's very easy to see that if 0 is stable, then asymptotic nilpotency implies nilpotency. So that's a very easy case. But note that we were using the fact that z can be split in two ways into a direct product. This is something we will not have in general. On the other hand, if information can spread arbitrarily far from one of these groups, suppose it can spread arbitrarily far from the vertical group, then there's a kind of funny shoot and kill by periodization argument, which goes like this. You assume that information can spread far from the vertical subgroup. Suppose it can spread here. Okay, so now you periodize in the vertical direction and you get a one-dimensional cellular automaton, but you still see the spreading before you see any difference because you take a very, very large period. So information spreads here, but now it's periodic, so actually it disappears eventually by nilrigidity in one dimension. So you were able to shoot something here, and then you were able to kill the configuration. But now, because this happens on all scales, you can shoot something from very far away and shoot it in the same position, and then you take another even bigger period and you kill that too. And then you just repeatedly shoot things at the origin, and you always kill this thing by adding a huge, massive period. And that contradicts asymptotic nilpotency. So that's the basic idea of the 2012 argument. But you see that there were a couple of things here which don't generalize to group extension. Okay, so now the idea is to take a large family of dynamical systems. They should be tiered dynamical systems is really the family. So it's somehow more than just dynamical systems in some sense. So the idea is that let G be K by H, and then we try to prove a result to G by sort of induction. But we need a certain kind of, and now the question is, what do we need to know about systems on K and H to be able to deduce nilrigidity for endomorphisms of K actions from those of these two? And then we do the same case analysis. Suppose information cannot, so suppose that we are dealing with a cellular automaton on, for example, A to the G, because everything already appears there. If information cannot spread from the subgroup K, so recall that in this definition, K is a normal subgroup, then there is no other direction. And again, so that means that we cannot use the same idea as in Z, that we look at two different rotations of Z. There is no other rotation. There is just the one normal subgroup. So there is now no natural K system which is stabilized by F, but there is a natural stack of K systems, which mean that I will try to define them in the case of the Heisenberg group, maybe in a few seconds. And then there's the other case. If information does not spread, if the information does spread from K, then we use the periodization argument, and the argument works almost verbatim. But this is where we need the stack of group homomorphisms just for technical reasons. And these are the fix and fin constructions. So the fixed construction is periodization in a lattice in K, and fin is the shoot and kill stuff. So in the case of the Heisenberg group, so this is A, B, C. C is the commutator of A and B, and then C commutes with these two. So it's a Z extension of Z squared. central extension. Now, cellular automata and the Heisenberg are nilrigid. So the rough idea of the proof is, suppose that you have a cellular automaton which is asymptotically nilpotent. You define a tiered dynamical system as follows. You take xt to be those configurations where there is no information further than t from the central subgroup. So you have the central subgroup spanned by c, which for me is from bottom to top, and then you take a tube around this subgroup, and that's what we call xt. And here the action. So this is the left invariant metric on the Cayley graph. So those g which are not further than t from the central subgroup, there you should have zeros. So and then you take, so the tiered dynamical system is that you take the naturals and you let the groups always be z. So all of these groups act by just the central translation, so translation by c, and then you get a tiered dynamical system, just because this assumption implies that all the vertical translations are expansive. That's more or less all you have to check. And now, if information cannot spread arbitrarily far from the central subgroup, then you have stabilization. You have that if information is originally in the t neighborhood of this central subgroup, then the definition of information not spreading is literally that it does not spread further by more than some finite bound. So we have stabilization, and now you have a stabilizing ETDDS. So in this case, we can apply the nil rigidity of z ETDDS to obtain the result. And here I haven't said what the exact kind of nil rigidity result is. It is a very strong result in the case of z that we have. You can see the exact statement if you look at our paper. In the case when it's not f stabilizing, here again, this is rather easy in some sense, but it shows you why we need the group extensions, the group homomorphisms. So here we take c to the t as generating a normal subgroup. So you take bigger and bigger lattices in the group generated by c, and you take this guy, so the integers under divisibility as the tiers, and then you take gt to be h3 quotiented by this normal subgroup kt, and then you have just the natural maps between these groups, right? You just quotient out more and more. And then you define xt as the periodic points in the c direction, which makes sense because it's a normal subgroup. And now you get another tiered dynamical system. And now the thing is that in the case of z, when we periodized, we used the horizontal translations as the kind of orthogonal action. Here we don't have an orthogonal action because z squared is not actually a subgroup of h3, it's just a quotient. So instead we quotient, and we get these quotient groups which act. So the base group is that we actually periodize by period 1, and that's z squared. And that's but in general, your group will be literally h3 quotiented by this period. So you really need a bunch of different groups. So here f stabilization is trivial by just shift commutation, and then you mimic the shoot and periodize argument from z squared, and this will give you that an implies nilpotency. Okay. So that was actually all I wanted to say. So the rest, I know it was pretty quick, but I wanted to tell you a bit about the proofs because it's hard to understand the motivation for all the technical things we do without knowing sort of what we are trying to generalize with them. To conclude, here's a few questions. Are cellular automata nilrigid on full shifts on all groups? We did a bunch of groups, but not all of them, and maybe even in all SFTs with dense homoclinics. For example, in all strongly reducible SFTs, that would be very interesting to me. A particularly interesting case is the free group. We don't know if cellular automata are nilrigid on the free group. Here's another example that was not covered, which I mentioned. And I think that we don't cover residually finite elementary amenable groups. I actually had an example, but Ilkka pointed out to me that my example was solvable. So actually, I don't have an example here, which we don't cover. And then you can also ask about the positive dimension. We don't have very interesting applications in that case. And then you could also ask, maybe in 2 dimensions, are cellular automata nilrigid on all z-squared SFTs? We only have this if the periodic points are dense. And finally, some limitations. We know in Z that in Z SFTs, cellular automata are nilrigid, but on suffix this breaks, so you cannot go from SFTs to suffix. There are Z suffix, which are very nice, and still cellular automata are not nilrigid. Then I asked if maybe in Z² all SFTs are nilrigid. Okay, we know that this is again not true in Z3. In Z3 you do need the dense homoclinic points assumption. There are cellular automata in 3 dimensions on SFTs which are not nilrigid. And then also I asked about the free group. I know that if you take the full automorphism group of the infinite k-regular tree, then the endomorphisms of this system are actually nilrigid. Okay, so that's all, and I say thanks, and maybe I leave the questions here because maybe you want to answer them. Okay, that's all.